For years, the smart home has been a fragmented mess. A patchwork of proprietary hubs, vendor lock-in, and protocols that simply don't talk to each other. We've all been there. But there's a new standard, Matter. And today we're not just talking about the consumer side. We're going to architect and build a production-grade, enterprise-ready Java Microservice that functions as a fully autonomous, headless Matter controller. This is the future of scaled, independent home automation. Stay tuned because the journey from a C++ SDK to a resilient Spring Boot application is a fascinating engineering challenge. Matter's brilliance lies in its simplicity. It's a unified application layer built on the Internet Protocol, specifically IPv6. This is huge. It means no more proprietary protocol gateways. Your Java microservice communicates directly with Matter devices over the standard LAN, simplifying the network topology dramatically. In the Matter world, any addressable entity is a node. Our microservice takes on the role of a controller, a node with the cryptographic credentials and permissions to commission and operate devices. Most of the current controller examples are in mobile apps. Android, iOS. They're transient and user-centric. Our goal is a headless controller. It runs 24/7 as a background daemon, containerized service. This means our microservice must 1. Maintain a persistent state. 2. Manage cryptographic identities securely. 3. Handle the full lifecycle, discovery, commissioning, and command invocation without human intervention. This is why we choose Java and Spring Boot. We need enterprise-grade resilience, monitoring, and integration capabilities that a server-side framework provides. Now for the biggest hurdle, the Matter reference implementation. Project Chip is a massive codebase written in C++. We need to bridge this high-performance native core to our JVM. This is achieved via the Java Native Interface, or JNI. The Matter build system uses tools common in the embedded world, GN and Ninja. This is alien to the typical Maven/Gradle Java ecosystem. Since the Java bindings are not published to Maven Central, we must compile them ourselves. The process starts with the right environment on a Linux host. You need libssl-dev for crypto, libdbus-1-dev for the BlueZ Bluetooth stack, and the compatible JDK. Then you use gn to configure the build. The crucial command is gn genout java controller --rx equals target_os equals Linux, target CPU equals x64, build Java Matter controller equals true. We're explicitly telling it to target Linux, our server architecture, and to build the specific Java controller logic. After running ninja-c out java-controller java-matter-controller, we get our two artifacts, libchipcontroller.so, the native library, and matter-controller.jar, the Java classes. Do not force every developer to build this. Publish these artifacts to an internal Maven repository, like Nexus or Artifactory. This decouples the complex C++ build chain from our Java microservice development cycle. Moving to the application layer, Spring Boot provides the managed runtime. The chip device controller is the entry point. It's stateful, maintaining a handle to unmanaged C++ memory and the active fabric state. You must implement it as a singleton bean. Instantiating multiple controllers for the same fabric will cause port and state conflicts. Loading the native .so file is a critical, fragile step. While you can rely on the system's java.library.path, a more robust pattern for containerized fat jars is to 1. Extract the .so file from the jar's resources to a temporary runtime directory. 2. Load it using system.load. This makes the microservice truly self-contained and portable across Linux environments. The Matter SDK operates on its own internal high-speed Matter event loop, a critical constraint. Any Java code executed within a Matter callback must not be a long-running blocking operation, or you will stall the native loop and cause protocol timeouts. The architectural solution is a bridging mechanism. When a callback comes in, offload the data immediately to a Spring-managed task executor or a reactive stream like Project Reactor. This decouples the latency-sensitive Matter protocol from your potentially blocking business logic, database writes, external HTTP calls, etc. Unlike many REST services, a Matter controller is inherently stateful. Lose the state and the controller loses its identity, forcing a factory reset on all devices, a catastrophic failure. The Matter SDK abstracts storage through the Key Value Store Manager interface. In a server environment, we toss the mobile-centric shared preferences and implement a durable server-grade backend. Redis is an excellent fit for its speed and native key value structure. Postgres can be used for asset compliance and easier backups. Your adapter implementation must be thread-safe, as the Matter stack can trigger storage operations from multiple native threads. By using an external database, the microservice itself becomes stateless on the local disk, allowing for seamless Kubernetes deployment rollouts without losing the fabric identity. Matter security is built on public key infrastructure. The most critical asset is the controller's private key. The SDK provides the key pair delegate interface as a critical extension point. The default implementation of storing keys on the file system is not acceptable for production. By implementing key pair delegate, we can offload private key operations to a hardware security module or a cloud-based key management service like the HashiCorp Vault. When the Matter stack needs to sign a message, the delegate sends the hash to the secure enclave and the signature is returned. The private key never leaves the secure boundary, providing significant hardening against exfiltration attacks. We've established what this Matter microservice is. Now let's look at the critical architectural advantage it provides over the legacy solutions we've all been using, specifically a hybrid of ZigBee and MQTT. In the old model, a ZigBee device, chosen for its low power consumption and good device market, is non-IP. It speaks a different protocol. To reach your enterprise logic, you need a dedicated physical coordinator or hub. This hub required a specific radio dongle and a separate piece of software, like ZigBee to MQTT, to run on a gateway machine like a Raspberry Pi. This creates three major components just to translate a single command or sensor reading. Matter eliminates this architectural layer entirely. Since it's built on IPv6, the device is a native network participant. Our Java microservice speaks to the Matter device directly over the standard LAN, simplifying the network topology dramatically and removing the single point of failure that the dedicated protocol gateway represented. MQTT, while excellent, was historically necessary as the central nervous system to bridge the ZigBee gateway to your actual automation logic. The device data went ZigBee radio to ZigBee to MQTT to Mosquito MQTT broker to OpenHAB or your other application. You had to manage the broker, the topics, and the data schema manually. Matter collapses this too. Matter's subscription model is its own built-in real-time message broker. When a device state changes, it proactively pushes an attribute report directly to our controller over IP. This is event-driven, just like MQTT, but it's native to the protocol itself, reducing the number of external systems you have to deploy, monitor, and maintain. In the Matter world, we can still use Kafka or external MQTT, but only as a generic enterprise event bus, not as the sole method of communicating with the devices themselves. How do we get devices onto our headless server? Forget about server-side Bluetooth Low Energy. The most robust strategy for a pure software microservice is the multi-admin pattern, also known as the secondary commissioner. The multi-admin workflow. 1. The user first commissions the device using a mobile ecosystem like Google Home or Apple Home. 2. The user then uses the app to generate an 11-digit pairing code. 3. Our microservice exposes an API endpoint to receive this code. 4. We call chip-device-controller.pairDevice node ID pairing code. This is brilliant. It offloads the difficult Wi-Fi and Bluetooth provisioning to an optimized mobile OS, allowing our Java service to focus solely on the high-level orchestration and logic. Device interaction is governed by the Matter data model: nodes, endpoints, clusters, and attributes. The Java classes for clusters are code-generated by the Zap tool, not handwritten. This gives us methods like on/off-cluster.on.
For real-time automation, we must use subscriptions. Polling is inefficient and discouraged. Our microservice establishes a subscription for critical device attributes, like a sensor's occupancy. The device then proactively pushes a report to our controller when the state changes.
This is where the magic happens. We translate the low-level Matter protocol onto generic enterprise events. Ingress. Listen to a Kafka topic, for example, home.commands, for high-level requests. Example, device light1 action on. Resolve the node ID and invoke the Matter command. Egress. Publish the real-time attribute reports from subscriptions to an egress topic, for example, home.events, for consumption by rule engines, analytics services, or user dashboards. And finally, to avoid the visible delay when controlling multiple devices, the popcorn effect, always use Matter groups to send a single multicast command that executes synchronously across all devices. By compiling the native SDK, wrapping it in a resilient Spring Boot container, and implementing hardened adapters for persistence and security, we have built a future-proof automation platform. This architecture delivers independence from vendor clouds, scalability using enterprise patterns like Kafka and Redis, resilience via local-first execution. The Matter protocol is the open standard we've been waiting for. The engineering work is complex, but the result is a robust, production-ready system. If you found this deep dive useful, hit that like button, subscribe for more advanced engineering content, and check the description below for links to the Matter GitHub repo and the conceptual architecture diagram. Thanks for watching.